Okay, so welcome back to the weekly live sessions on real mobile robots. So today we discuss all the topics from week 8 lecture series. So it will also be the final week for the course because real mobile robots is basically an 8-week course, right? So I'll give you a brief summary of all the topics that we have covered until now. So on week 1, we have covered basic kinematic modeling of a wheel mobile robot for various configurations of the mobile base. And week 1 and 2 were both dedicated for kinematics. Week 3, we have also covered the dynamic modeling of various configurations of mobile robot and how the placement of different kinds of wheels on the robot chassis would influence the dynamics of the mobile robot. So that was week 3. And for week 4, we have covered the basics of perceptions. We have also seen the workings of different kinds of sensors that is relevant to real mobile robots. And on week 5, we have covered the topics on localization. Like, for example, like if the robot is seeing currently through its sensor, if it is perceiving its environment, once perception, then it should also locate its relative position on a map that is being built by the robot. So that is what localization is all about. And once the localization is done, the robot will be able to figure out how to get to a goal position from its current location. And on week 6, we have covered navigation, topics regarding navigation. And on week 7, it was mostly about motion control. We have actually discussed different kinds of motion control, be it kinematic control, be it dynamic control. We have also seen open loop and closed loop implementations of kinematic as well as dynamic controls. And week 8, which is what we would be discussing today, is more or less a general overview of various other kinds of mobile robots. So this course was mostly focused on wheeled mobile robots. But apart from that, you would also know that mobile robots is actually an exhaustive term. It includes systems such as underwater mobile robots. We also have unmanned aerial vehicles. And then what do we have? Like instead of locomotion, instead of wheels, we could use tracks. We could also use legged locomotion. So these are all the different kinds of methods that we would use for robot locomotion. And we have covered a lot of topics for this week in brief. So the purpose of this session is just to briefly recall what we have covered through the entirety of this week. And I won't be going through much detail because all the lectures are more or less descriptive. It's self-explanatory. But however, for the purposes of this session, since we are also required to solve some sample problems, just for the sake of clarity, I would like to reintroduce you to some of the topics that we have covered during week 8 lectures. Okay, so week 8, we begin with our discussions on multiple robotic systems where instead of a single robot, multiple robots collaborate to do a specific task. So again, multiple robots is also an exhaustive term. There could be homogeneous robots that is actually participating in that robotic system. Homogeneous robots in the sense each and every robot is exactly identical uh, uh, based on all the other specifications. Like for example, if you consider a multi-robotic system consisting of all drones, the drones alone, each and every drones would be identical with each other. And there are also multiple robotic systems where the robots are heterogeneous. There could be substantial differences between the participating robots within that multi-robotic system. So we'll consider the features and peculiarities of each of these different kinds of systems. Okay, so we will start our discussions with the common motivations regarding multi-robot systems or multiple robotic systems. So, like for example, the one of the The first point is the task complexity is too high for a single robot to accomplish. Like, for example, like if you have observed how ants, basically team up together to carry some of the food particles or something that is left over, you can actually observe how coherent they are actually, uh, how precisely they basically coordinate among each other so that they can basically navigate a payload that is much higher than their uh, individual weights to a target position. So multi-robots also do something similar, and the application is also something similar. Like if the task complexity, for example, if the payload is too high for a single robot to accomplish, we could employ multiple robots to collaborate in order for us to achieve this single objective, right? And the second point being, if the task is inherently distributed. For example, if the task can be inherently distributed, like if it is not a task that can be carried out by a single system or a single robot, it can be inherently distributed to uh, each and every members of a multi-robotic system. Then such tasks can also be delegated to a multi-robotic system. And third one being, building several resource-bound robots is much easier than having a single powerful robot. For example, if you are trying to do a task with a single powerful robot, it would be like, as the complexity of the tasks goes, the increase of complexity and designing of a robot powerful enough to realize that task is not linear at all. Because after one point, if the task complexity is actually getting more and more complicated, designing of the robot gets much more exponentially it's much more difficult, exponentially difficult, if the task complexity is also increasing. So in that regard, it would be very easier to delegate this task to a multi-robotic system where each and every constituent members of the multi-robotic system may not be that powerful, right? And another advantage is that, like, once we have designed a robot, it can be easily replicated, right? Once a simpler robotic system is actually developed, it can be easily replicated because we already have designed it. We can easily replicate it to function of, or to make them function as a multi-robotic system. The only thing we need to take care about is how they integrate with each other. But if you're delegating everything with the everything to a single and more powerful robot, designing something that is so powerful would be a huge deterrent, because the actuators themselves cost a lot of money. The design problem itself would be too complicated if the task is also uh, if the task is also be beyond reasonably if it cannot be solved within reasonable resources, right? So that is one of the reasons why we use multi-robot systems. And the fourth point being, multi-robots can solve problems faster using parallelism. So again, some of the tasks, some of the tasks probably you can do it in parallel. You don't have to wait one of the tasks to complete for the subsequent tasks to be taken care of. It can be run in parallel. Like, for example, if you want to assemble, uh, for example, if you consider a warehouse, if you have multiple products or multiple parts to be assembled into a single bin, if you are deploying a single robot, the robot will have to go to each and every counter or each and every shelves to bring back, to bring all these parts back and assemble. But if you're delegating this to a multi-robot or a robots of a multi-robotic system, each robot can actually go independently to the respective shelves or to the respective parts bin and bring back their corresponding parts into that final assembly bin. So that decreases the packing time considerably a lot, and that is also much more efficient. And since the task is actually independent, since like deploying each and every robot to a different location is basically independent of each other, you can do that as well. You can parallelize such kind of applications. So that makes solving problems much faster. But what I have given is actually a simple example. There are better examples. There could be better examples where parallelism could be, a huge asset. The fifth point be the introduction of multiple robots increases the robustness through redundancy. For example, if you consider an example of a GPS system, GPS would require at least around 24 satellites. The system actually consists of 24 satellites. And there are also other standby satellites, redundant satellites. So in case if any of these robots get damaged or if it goes out of service, the redundant or the spare satellites can take the defective satellite space. The same thing can also be set for a multi-robot system. Like if you are deploying a multi-robotic system, there are also a spare or redundant robots within that system, so that like if one of the robots go out of service, it can be easily replaced. So that basically increases the robustness of the system, robustness to failure through redundancy. Like we deploy maybe more number of robots that it is needed. So like once a robot goes out of service, it can be easily replaced. Right. So these are the common motivations motivations for deploying multiple robotic system or multi-robotic system to solve a specific task. And yeah, we then next talk about the classification of multi-robotic system. The first branch being collective swarm systems. For example, a real life example would be how the honeybees navigate among themselves. It's basically a swarm of. You can also carry out that similar analogy to robots, where the robots would be homogeneous. So the defining feature of swarm robots would be they are homogeneous. So each and every constituent robot within a collective swarm system would be exactly identical amongst each other. So, like for example, you could use this for surveillance, for search and rescue operations. Deploying multiple robotic system into a disaster struck area for ease of surveillance. And these days, you might have also seen these things used as uh, drones it's purely for entertainment purposes. You might have seen in videos where these light up drones actually form a structure or figure in space, and that is actually purely based on this collective swarm system. These collective swarm system, it's about making them coordinate with among each other. And the second class is basically intentionally cooperative system. So this part consists of heterogeneous robots where each and every robots within the subsystem may or may not be separate from each other. Like each and every maybe one robot have other have a manipulator arm, maybe a 60 degrees of freedom manipulator arm, and this maybe another robot within that same multi-robotic system can have different capabilities. Maybe it could have a different manipulator of a different configuration. It could have a different set of sensors. So anything could be different. It does not really have to be homogeneous. And within this intentionally cooperative systems, you also further, it can be further classified into weakly cooperative systems and strongly cooperative systems. So we'll basically see what we mean by weakly cooperative systems and strongly cooperative systems in the subsequent slides. Okay, so we'll cover the details of the classification one by one. So the first one was uh, collective swarm systems, where we say that it comprises of homogeneous multiple robots. And the first point being robots execute their own tasks with only the minimal need of knowledge about other robots, other robot team members. So, like for example, even if they need to coordinate among each other, only their tasks need to be delegated to a specific robot. The robot does not have to know what other robots are doing. So like if you want all the robot to collaborate or to do a coordinated task, you only need to download or upload a specific instruction to a robot alone. You don't have to let the robot know what other robotic systems are actually doing. So that is one of the features of collective swarm systems. These systems are typified by the assumption of a large number of mobile robots, in which a robot makes use of local control laws to generate a globally coherent team behaviors with little explicit communication among each other. So each and every robot will have its own local control laws. It does not really need to know what other robots are actually doing. And as a result, it does not have any sort of communication or sensor capabilities so that it can communicate with the same robots within that or other robots within that same system. So that is one of the features of the collective robot. And the next being intentionally cooperative systems. So the first point being they have the knowledge of the presence of other robots in the environment and act together based on the state, actions, or capabilities of teammates in order to accomplish common goal. So in this case, each and every robot will be aware of what are the capabilities of other robots within that system. Like for example, if they need to perform a yeah, we may have some connection issues. Let me see if I can rectify that. Okay, apologies for the delay. Yeah, I hope I'm visible. So we'll continue. Yeah, in case of what do we say? Yeah, in case of intentionally operating systems, the robots have the knowledge of the presence of other robots within this environment. Like as I was saying, each and every robots are aware of the capabilities of all the other robots within the same system. So, like for example, in order for them to carry out a common task, some of the robots it may require a particular sensor or it may require some sort of an actuator. So whichever robot has that actuator, it will have to do that task. So it will have to keep on adapting. And maybe some other robot within that system would be coordinating all the other robots within that system. And if the coordinating robot knows a particular robot has a sensor for a specific application, then it can actually delegate that robot with a particular sensor to do that task. And if it wants to carry out some action, maybe some other robot may have that particular actuator. For example, if it is required to take an object and place it somewhere, based on the information it got from other robots about the position of the object, the the central robot can actually delegate robot which has that specific actuator to carry out that particular task. So in that regard, in case of an intentionally cooperating robot, the robots are more or less aware of the capabilities and the functions of all the other robots or their teammates within that system. And their level of cooperation actually vary in the extent to which robot takes into account the actions or state of other robots and can either lead to weakly or strongly or weakly cooperative solutions, right? So depending on the state of other robots or the type of uh, application that they are being deployed to, we could have two different kinds of intentional cooperation called as strongly cooperative systems as well as weakly cooperative systems. And going further deep into either of these cases, in case of a strongly cooperative solution, it requires the robot to act in concert to achieve the goal in executing the tasks that are not trivially serializable. Like, so it requires all the robot to, you know, to act in concert. Like, what happens in the concert, like each and every constant elements should act in coherence. So this is what basically a strongly cooperative system is all about. And we also make deploy these sort of systems on tasks that is not serially trivializable. For example, tasks that need to be carried out in parallel. For example, if it, for example, something as simple as lifting a large payload, you may need all the robots to coordinate appropriately to lift that specific payload. No, the appropriate, the point of application of the loads or point where each and every robot grasps this particular payload. These are all important actually, and it has to be done in concert. It has to be balanced as well. So if the payload is not properly balanced, it may fall over and the task may not be carried out satisfactorily. So that is why we require all the robots within that system to act in concert or to act coherently. And they require some type of communication and synchronization among the robots. And what about weakly cooperative solutions? So in this case, they allow robots to have periods of operational independence subsequent to coordinating their tasks, coordinating their selection of tasks or roles. So very much unlike to the strongly cooperative systems, in weakly cooperative systems, the robot can have period of operational independence. So for example, if it need to do a task on its own without the help of or without the assistance of its teammates, it can carry out its own. It does not need any of those approval of or any of the any sort of delegation from any other robot within that team. And these systems can deal with heterogeneity in the robot team members. So they can basically deal with heterogeneity much better than strongly cooperative solutions, in which team members vary in their sensor and effector capabilities. The third point being the coordination of robots can be very different from collective swarm approaches, since the robots are no longer interchangeable. So that makes it even a difficult problem. For example, in case of a collective swarm robots, they may form a formation. Like for example, if the task is to form a formation, something like this. This is robot 1, robot 2, robot 3, robot 4, robot 5. This space is basically a collective swarm robotic system comprising of 5 robots. And the task is to form a configuration like this, a diamond-like configuration with a robot at the center. So even if we interchange these robots, for example, 1, 3, 5, 4, 2, even if we interchange the positions of this robot, it does not make any difference, or it does not really make any difference, because each and every consistent robots within a collective swarm system is homogeneous. So it does not matter if their orders or if their relative locations are changed. But in case of a weakly cooperative system, since each and every one of these constant elements are heterogeneous, they are not identical to each other. Changing their configuration will definitely make a difference. It's not as same as in the case of a collective swarm approaches. So in that regard, the coordination of the robot in a weakly cooperative solutions can vary, or it could be completely different based on the case of collective swarm approaches. Okay, now we move on to the different control architectures of mobile robot. And the basic summary of all the things that we have discussed during the lectures can be summarized using these two bullet points. So it says the design of the overall control architecture for a multi-robotics team has a significant impact on the robustness and scalability of the system. So robustness more or less basically means robustness to failure. So like for example, if one of the robot is out of order, can that multi-robotic system still perform the task it has been asked to do so? That is what this robustness basically deals with. And scalability means like if the task was originally much smaller, can it be easily scaled up to a task that is task that is equally scaled up, or it could be even maybe in case of complexity, it could be similarly scaled up. Could that be made possible? And in that regard, we have several different philosophies for multi-robot system architectures, and we have the following four architectures, which are called centralized, hierarchical, decentralized, as well as hybrid. Again, looking through each of these architectures. So in case of a centralized control architecture, what it does is that it coordinates this entire team from a single, although often practically unrealistic, from a single point of view, actually, from a single server or a single server. Maybe I have missed that detail over here. From a single perspective, although often practically unrealistic due to their vulnerability to a single point of failure, and due to the difficulty of communicating the entire system state back to the central location at a frequency suitable for the real-time control. Like for example, in case of a centralized robot, each and every functions or activities of the constituent robots or the constituent teammates will be monitored by a central robot or maybe a central server. And what happens is that, like in the situations in which these approaches are relevant, are cases in which the centralized controller has a clear vantage point from which to observe the robots and can easily broadcast group messages for all the robots to obey. So this centralized controller will be at a vantage point, or a point where it can easily observe or it can easily delegate tasks to each and every robot within that system. And when required, it can also send broadcast group messages or broadcast commands to each and every members of that multi-robotic system. But the problem with centralized system is that, like, if there is a single point of failure, the entire system crashes. Entire system ceases to function. Right? In case of, and if the server itself fails, then the entire task or the entire process will have to be halted until and unless the server is restored back into operation. So that is what this centralized architecture is about. Just like its name states, there is a centralized central control system that that does the surveillance for each and every members of the robotic system. The second being this hierarchical architecture. So in this case, in this control approach, each robot oversees the action of a relatively small group of other robots. And each of the robots in turn oversees yet another group of robots, and so forth, down to the lowest robot. This will simply execute its part of the task. So just like what we see in organizations, so it will have a top level robot, and the task will be delegated to the robots at lower level, and this process basically carries down. It will be further and further delegated until it reaches to the robot at the lowermost tier, which would be doing its its job or its task. And it also says that this architecture scales much better than centralized approaches and is reminiscent of military command and control. Just like how the hierarchy works in military, command, we have probably at the highest, we may have a captain, then comes the lieutenant, sub-lieutenant, and all those. So it's more or less similar to a military, uh, you know, hierarchy in military command. And third point being, point of weakness for the hierarchical control architecture is recovering from the failures of robot uh, high in the control tree. For example, if a robot is failing at the lowermost tier, only this function would be affected. And all the other sub channels or the other sub branches can function without any fail. But if something that is at the very high fails, or if maybe the topmost robot fails, then it won't be able to send any of this information to the subsequent level. So this entire system crashes. But if something at the lowermost level crashes, all the other systems can function without any interruption. And if the task can be, and since if a lower level robot is failing, it can also be easily replaced with a robot of a similar specification. That wouldn't be much of an issue. And the restoration of this entire process to 100% can also be easily carried out, which is quite unlike the centralized architecture, like where if a robot fails at any of these uh, uh, anywhere, the entire system basically ceases to function, which is not the case in hierarchical architecture. Then the third one being decentralized architecture. And this is the most common approach for multi-robot systems and typically require to take action based only on the knowledge local to their situation. Right? So it does not need any sort of orders or commands from robots higher up its hierarchy. What it should be doing or what it is supposed to do is already being fed into it. It already is embedded into it, or it's been already been communicated. So it does not really need to know what others are basically doing, and they themselves are aware of the task that they need to execute. And this control approach can be highly robust to failure since no robot is responsible for the control of any other robot. Like, since there is no definite hierarchy, so like if a robot fails, it does not need to report or it does not need to send commands to the robots that is at a lower level to that failed robot, or it does not need to pass any information to the robots that is at a higher level. And in case of centralized robots, since these are all not coordinated, or since the robots themselves are not communicating with each other, only the robot that is failed is responsible for it, that failure. It does not really have to be affecting this entire system. So in that regard, if the robot is easily replaced, if the failed robot is easily replaced, this entire system can be easily restored back to its 100% functionality. That is the one of the points. The third point being achieving global coherency in these systems can be difficult because high level goals have to be incorporated into the local control of each robot. So these are mostly ideal for doing tasks that require very least complexity, right? Because it lacks a centralized or it lacks a central robot or a central server which can coordinate all the other robots down its hierarchy. But since in case of a decentralized robot, since each robot is on their own or is for themselves, it'll be very difficult for them to coordinate because they are only caring about or they are only being fed about the task that they are supposed to do. And if you require some sort of a synchronous task or some sort of coherency, then this high level code will have to be deployed into each and every robot within that multi-robotic system. So that makes them incredibly complicated and unnecessary because if tasks that may not be even relevant to that specific robot will have to be uploaded so that it can be coordinated. But again, that makes it unreasonably complicated, right? If you are feeding all these high level commands into each and every robots into that system. And if the goal change, it may be difficult to revise the behavior of individual robots. Like since we are deploying the high level codes into each and every constituent members, if if our goals changes or if our application changes, then each and every robot within that robotic system will have to be reprogrammed. Otherwise, if it were a centralized or hierarchical robot, we only need to do this once, at the robot that is at the highest commanding position. But when it comes to centralized, since each robot is for themselves, we'll have to reprogram each and every robot at a very high level. So that makes it even more inefficient for such tasks, such tasks that require no global coherency. And the final one be hybrid architecture. So as the name suggests, it's basically a hybrid between decentralized and centralized approaches. So it combines the local control with high level control approaches to achieve both robustness and ability to influence the entire team actions through global goals, plans, or control. So it is basically a hybrid of decentralized architecture. So the robustness, right? The robustness comes from this decentralized architecture. Robustness to failure comes from hybrid architecture, and the ease with which we can influence all the team members' uh, goals through a single point of view, or maybe through a single command. Ability to influence the entire team's actions through a global goals. These are basically taken from hierarchical architecture or centralized architecture. So we have both the advantages of decentralized and hierarchical or centralized in hybrid architecture. So like the task can be easily delegated, and the entire behavior of the system can be easily reprogrammed. And it is also highly robust because it also has the defining features of decentralized architecture. Right. So in that regard, many multi-robot control approaches make use of hybrid architectures because of their ease of reprogrammability or ease of programmability, as well as their very high robustness. Okay, then in subsequent lectures, we discuss briefly about autonomous mobile robots as well as mobile manipulators. So in brief, we have mobile robots can be basically classified into two. The first being autonomous mobile robots or AMRs, and the second being automated guided vehicles. So what are the differences between AMRs and AGVs? So that is what we are covering in this slide. So in case of an AMR or autonomous mobile robots can be AMRs, which means they are capable of navigating an uncontrolled environment without the need of physical or electromechanical guidance device. So like just for example, similar to what we have covered during week 4, week 5, and week 6 lectures, AMRs have inherent sensors or abilities to perceive the environment around them. And they can also navigate, on their own without the need of any external intervention or probably human intervention, based on localization and navigation, the topics that we have covered in the previous weeks. So yeah, and it can navigate on its own. Like if you are inputting some input command, and if we are also specifying a goal position, and maybe if you are also delegating it to do a specific task at a goal position, the mobile robot is capable of executing each and every one of these commands without any human or external intervention. Whereas in the case of automated guided vehicles or AGVs, mobile robots can rely on guidance devices that allow them to travel a predefined navigation route in a clearly controlled space. Right. So in case of AGVs, we basically lay the tracks, predefined tracks. So unlike AMRs, it can navigate on its own on a controlled environment. Whereas in case of AGV, they are deployed on controlled space. For example, in warehouses and other industrial applications where it's more or less is a controlled or a confined space. And we also lay them tracks, predefined tracks. And we also, using the sensors, we also make the robot follow this specific track that is relevant to its task. a predefined navigation route. Like there are plenty of ways that we can define this navigation route, right? For example, if we are fixing a black tape on a floor, and by using this uh, IR sensors, we will be able to track this black tape or a black line. Whether it is actually going through the black line or whether it is going out of this black line. We can essentially guide a robot through, the this black line. If we are actually sticking a tape on the floor and using the inputs from an IR sensor, we can make the robot track this, black strip, or in other words, this predefined navigation. So that was the difference between AMRs and AGVs, and it can also be consolidated through these points. So in case of one, fixed routes versus intelligent navigation, right? So in case of AGVs, they use fixed routes. AGV use fixed or predefined routes. Whereas in case of AMRs, they basically do their navigation on their own. So they have some sort of an intelligence inbuilt on them. And AGVs are only intended for a few applications. For example, if the robot is programmed to go along a fixed path, it can only be used to tasks that requires the robot to go along the fixed path. Otherwise, it will have to be severely reprogrammed or remodified. But in the case of AMRs, they have very high flexibility because with minimal effort, it can be programmed to do an entirely different task because it has its own sensor capabilities. It has its own competitive actuators, and it also has intelligent algorithms inbuilt in them so that it can easily adapt to a newly delegated tasks. And in case of AGVs, they are more suitable for traditional business models without any flexibilities. But in case of AMRs, they can be employed for agile businesses where the goals keep on changing, or maybe the tasks on which we deploy the mobile robot is basically highly dynamic. And in that regard, on a longer run, AGVs can be expensive because if your task is highly agile, every time you will have to, reprogram or reconfigure your AGVs. You may, take out some of the sensors, or you may need some more sensors. Whereas in case of an AMR, a simple reprogramming would be uh, only a simple reprogramming could be required in most of the cases. So that makes AMRs much more cost effective in the longer run compared to AGVs. Okay, now next we move on to mobile manipulator. So whatever we have covered during the course is also a mobile robot. Is also a mobile robot in that regard, right? It's in particular it's a wheel mobile robot, right? So when does it become a mobile manipulator? So when we mount or when we give some sort of motion capabilities to the base of a manipulator, then it becomes a mobile manipulator. How do we give this motion capability to the base of a mobile manipulator? One thing we could do is we could simply attach the base of a manipulator onto a mobile base. It could be a wheeled mobile robot, it could be an underwater vehicle, or it could be an aerial drone. So attaching a manipulator's base to either of these mobile robots, a wheel mobile robot, or an underwater vehicle, or an unmanned aerial robot, that could give you a mobile manipulator in effect, right? So the definition says a mobile manipulator is a robotic system built from robotic manipulator arm mounted on a mobile platform. And such systems combine the advantage of mobile platforms and robotic manipulator arms while reducing their drawbacks. So what are their advantages? So the advantage of a mobile robot or mobile platform is that they have unlimited workspace. Their workspace is actually not limited at all. And what are the advantages of a manipulator arm? So a manipulator arm can be deployed to do some of the tasks using its end effector. If you want to pick and place something, or if you want to pick something and orient in it some other configuration, you can make use of a manipulator. But as you know, in case of a robotic manipulator, most often the base of the manipulator would be fixed to a spot or fixed to the ground. So their workspace is more or less limited because one of the links is actually fixed. But if you are mounting that base to a mobile platform, then the limitations of workspace of a manipulator will not be existing anymore. Will be taken out. So yeah, it has the dexterity or the payload manipulability of a of a manipulator, and at the same time, this system will also have the unlimited workspace of a mobile platform. So that is what we mean by the second statement. Combining the advantage of mobile platforms as well as robotic arms, right? And the third point also more or less the same thing. For instance, mobile platform extends the workspace of an arm where an arm offers several operational functionalities, which a mobile robot cannot do on its own. A mobile platform cannot do on its own. And we'll talk about vehicle manipulators actually. So, a vehicle manipulator is a robot that is intended to operate with dexterity in a workspace larger than that of a fixed base manipulator and consists of two parts. Right? A vehicle manipulator is supposed to operate with dexterity. Dexterity means it can be able to reach a specific point in multiple orientations. For example, I don't know if you can see, if I hold this pen over the point, I can still, reach this point through any other orientation actually. So multiple sort of orientations are possible at this specific point. So that makes them dexterous, right? And a vehicle manipulator will also impart this manipulator a much larger workspace when compared with the case when the base was fixed to the ground. Yeah, and the two parts consisting of the vehicle manipulator are a base with normally with actuation, which can move freely in a given environment. Right? A base here we mean by what we mean by base is nothing but a mobile platform, right? The second point being one or more manipulator arms on the base. So we can have one or more multiple arms on the base. For example, if you want both of these arms to coordinate, we can still have multiple arms coming out from this mobile base. And the second point is what we have now covered. The base is what gives the VM its ability to locomote over what is on a large geographical area, right? So the base of the vehicle manipulator, that is the vehicle itself, is what is giving the capability to reach out to a larger area. The third point being the base can be a vehicle in normal sense, such as car, satellite, or underwater vehicle, or it can be another robotic device that allows for motion in a more restricted area, such as rail, gantry, or probably steward platform. I suppose these are all self-explanatory. The base could be a general vehicle, just like a car, or it could be any other robotic system. For example, a steward platform. You might know. It's something that we use to build flight simulators. It's a parallel robot, so we can mount our manipulator onto another robot like a steward platform. So it's much better than having the base of the manipulator fixed onto the ground. But in case if you are mounting that onto a steward platform, it can have much larger workspace. Okay, so that was about vehicle manipulators. Next, we briefly covered about leg locomotion. And as you can see, there are various kinds of leg locomotion. Over here in this figure is quadruped. Probably mimics how a dog or probably an animal, a cheetah or a mammal walks, right? How a mammal basically commutes. And over here is what we call a biped, more or less similar to how humans walk. They have this humanoid walking pattern. And there are also other systems, mostly bio-inspired. Some of the legged robots are inspired from insects and bugs, where can have 6 legs, hexapods, It can have 8 legs, octopods, all those sort of things. So they all come under leg locomotion. And what are their features? So robots are type of mobile robot which uses articulated limbs such as leg mechanisms to provide locomotion. So articulated limbs in the sense these limbs, each and every element of these limbs are actuated using motors. And at the end of this link is what we call this foot linkage or the foot body, which can be used for the robot to locomote, about. They often imitate legged animals such as human insects, and in another examples of, and it's also another example of biomimicry. So the inspiration mostly comes from yeah, legged animals, mostly legged mammals such as dogs, cheetahs, or for quadrupedal robots, and in case of a biped robot, it's mostly inspired from humans, the bone structures of humans. And what are the advantages and disadvantages of legged robots? The advantages are they have of higher mobility. For example, if the surface is highly uneven, or if it is a rough terrain, then using legs or legged robotic systems are much more efficient compared with wheeled locomotion, right? And they have less effect on uneven ground. They have less damage on the environment because they leave very poor and a very small footprint. For example, if you are using a heavy track robot, they may demolish everything that comes under their tires. So they may leave some sort of an environmental footprint, whereas in the case of legged robots, they leave a minimal footprint. And they can also achieve higher velocity on uneven ground, right? Because if you are using a mobile robot on an uneven ground, it may not even be able to exert the required traction force to move along the direction it really wants because it won't be balanced. And in that regard, legged robots can, in theory or inherently, they can achieve much higher fast or higher speed on uneven ground. And they are also better. They also have better energy consumption inherently, because as you know, all the animals are, they evolve naturally with what we have, with legged locomotion. And that also proved to be much more efficient. It's also much more energy efficient, actually, to use uh, to use the limbs that we have, you know, as a part of our evolution. Actually. The other point being, legged robots are designed for locomotion on rough terrain and require control of leg actuators to maintain balance. And sensors are also needed to determine the foot placement and planning algorithms to determine the direction and speed of the movement. So, despite this being the preferred way of locomotion by the nature, it also requires a lot of work to make legged robot work. Because, as you know, our legged robot is, or a legged locomotion is inherently unstable because of the inertia of the links and more importantly, the mass of these things. So, like since the legs are articulated, each and every joints of a leg would be controlled using motors. And they have to be controlled in real time all the time so that the robot is at least statically balanced. It won't fall over, right? And the periodic contact of legs of the ground with the ground is called gait of the walker, right? The kind of moving pattern that we observe in how human moves, that is something we call as gait. And if you observe animals with multiple more number of legs, if, uh, for example, a mammal, maybe a cheetah or a tiger or a dog, they have different kinds of gait. One kind of gait for standing still. They have a different gait for trotting, or simply going with a walking pace. If you observe trotting pace, in case most of the time, they're diagonal legs are actually in phase, front left and rear right would be in phase. And during the other half of the gait, the other diagonal, maybe the front left and the rear right would be in phase. But when they are sprinting, when they are running, they adopt to an entirely different gait. The front legs would be in phase and the rear legs would be in phase, apart from the diagonal phase. So the animals have different kinds of gait that they could employ depending on the kind of motion that they are executing. Right. And in order to maintain locomotion, the center of gravity of the walker must be supported either statically or dynamically. Right. So one simple example is that, like, if you have a body that is supported at 3 points, maybe a chair, for example, if you consider the chair to be having, or for example, a table that have 4 legs. And if the center of gravity is basically falling within this polygon that is connecting all the 4 support points, and if it is falling somewhere within that support polygon, then basically means that that structure is indeed stable. But due to some external payload, or if you are putting some sort of a weight, and if you are shifting this projected center of gravity outside this polygon supported by all the 4 contact points, then it's not stable, and there is the structure or the table would definitely fall over. So that is about static stability, and dynamic stability is actually about keeping that robot from falling as the robot is moving, from one position to another. And static is when the robot is entirely standstill, when it is, holding its own position, whether it is balanced or not. And dynamic balancing is whether it can, hold its own without falling over as the robot is moving. So those are the two problems that we face, or we need to solve while designing a legged robot. And yeah, we also have we've also discussed a few things regarding underwater and aerial vehicles. And since those are all self-explanatory and descriptive, we won't be covering that in uh, this current session. I will directly move on to this healthcare robots, right? Which is basically the last topic for this entire course, right? And this healthcare robots can be classified as such. It could be surgical robots, where we could use robots for surgical applications. We could employ healthcare robots as exoskeletons, exoskeletons to enhance the capability of a human using artificial muscles and all those things, so that we can manipulate something that is too heavy for a human being. We can also use robots for rehabilitation, right, to restore the strength of the muscles and knees for for patients suffering from accidental trauma, or rather trauma from strokes. For example, if a person has suffered from strokes, there is a high chance that their functionality or their motor functions are lost. So they can be restored using appropriate physiotherapy, but it's always very demanding to find a physiotherapist to perform all these tasks. So we can delegate this task to robots instead of finding an actual physiotherapist. So that makes the process much more efficient, and the road to recovery becomes much more accelerated. So we can also deploy robots for rehabilitation, and we can also deploy them for care for patients, as well as hospital robots, maybe for assisting a nurse, or maybe for carrying these equipments, or for room services and all those things. We can deploy them as well. We can deploy the robots as such. And the main advantages of employing robots in medical fields are their excellent geometric accuracy. See, like, for example, there are some surgeries where we have to do, or where the doctor will have to do some operations or some tasks that is too delicate for a human arm, because a human arm cannot make that level of, cannot realize that sort of level of delicacy, or even that, delicate movements or movements that is accurate to the micron level. So then how do we do that? If that is the case, we can deploy or employ a robot that can function to, millimeter level accuracy or even micron level accuracy. And the surgeon can basically control that specific robot using a master robot. And the robot that is actually doing this operation could be a slave robot. So, whatever operations that is being carried out by a surgeon on a master device, it can be, scaled down or scaled down to the millimeter level precision onto the slave robot, which can accurately do the surgical operations. So yeah, robots can be constrained to have excellent geometrical accuracy, and that is one of the motivating points on why we use, robots on surgical applications. Because some of the surgeries could be very intricate. It could be somewhere where a human arm or a human hand cannot easily access, but a robotic arm can access. Maybe a flexible robotic arm can easily access. So that is one of the most important motivating factor for employing robots in medical fields. Other thing is, a robot is basically, you know, not faced by fatigue or, tiredness as a human being faces. It can carry out, multiple stints of, multi-hour surgeries without breaking a sweat. So that is one of the advantages. And they are also immune to ionizing radiations, which, could be a potential health hazard for the doctors who you know who, whom we would be replacing with the robots. And they can also be designed to operate many different scales of motion and payload. Right? A single system can be used to perform surgeries that require, accuracies in centimeters or millimeters level. For example, amputation and all those things. Those require huge payload and, large scale of motion. Whereas in case of surgeries that require delicate level of uh, accuracy or delicate precise movements, then the same robotic manipulator can also be scaled down to that level of accuracy. And the fifth being able to integrate multiple sources of numerical and sensor data. Right? It can have redundant information just as a factor of safety. It can use image processing. It can also use tactile feedback. All these will only further improve the safety of this entire procedure. And as a robotic system, it can flawlessly integrate all these aspects. And if it is feeling like it is actually, it's observing something that is, not as per, or something that should not be observed, it can be easily reported back to the surgeon, to warn him or to stop the procedure or something, things like that. And if it is solely done by the human operator, there is a high chance that, there could be a misjudgment, and it's also easily possible to make a mistake. But since we have data from multiple sensors, it also has a redundancy built into them, and that makes it much more robust to, failures or failures or other aspects actually. And there are limitations for medical robots, which are poor judgment of robots. So I think we still haven't deployed robots all their, entirely independent of human intervention, because they are still, they still haven't evolved to the level of judgment a human being can, level of judgment a human being actually possesses. So even if we have surgical robots, it still needs some level of human intervention, because we still haven't cleared their poor judgment, this aspect. And it could be very hard to adapt to new situations, because once they are configured to do a specific task, it'll be very hard to reconfigure them to do maybe a entirely different task. And some of the systems may have limited dexterity, because it may not be, sometimes it may not be fully delicate as a human arm, because we can, apart from manipulating objects within the space, in a space, we can also vary the stiffness of a human arm, right? We can also vary it based on how we contract our muscles. We can make the stiffness of the arm variable. But that level of delicacy, or that level of uh, variability cannot be really achieved by medical robots as of now. And limited hand-eye configurations. For example, like if we are manipulating an object, we can do that instinctively. But if we are forcing a machine to do some tasks that normally our hands could do, it cannot be as natural as how we do it with our own hands. So that comes in this point. And another thing be limited haptic sensing. For example, if you want to feel a feature or a specific part for patient, we can use our own hands, to see whether that specific part is tender, or it may have some sort of lump or swelling or something like that. We can feel it with our own hands. But with a robot, we cannot do that yet, because our haptic sensing capabilities are still quite limited. So we may not get the same level of feedback from a robotic system. And they also have limited ability to integrate and interpret common information. Because, for example, if you are supplying a robot with an MRI scan results or a CT scan results, it may not be able to interpret what it is actually seeing and carry out further tasks. So these things would still require human intervention, because robots as of now are not capable to do so. And there are, just like what we have discussed earlier, in case of health robots, we have different control paradigms. So yeah, the three control paradigms, the first being the pre-programmed or semi-autonomous motion. So in this case, the desired behavior of a robot's tool is specified by the surgeon. So if you want the robot's tool to move in a specified way, it can be easily specified by the surgeon, usually based on medical images. The computer then fills in the details and obtain the surgeon's concurrence before the robot is moved. Right. So, like if uh, probably the surgeon could be defining the movement in a discrete fashion, the computer can basically interpolate, what is being described by the surgeon, and once it actually plants this path, the robot will actually ask the concurrence of the surgeon whether should it execute this task which it has planned or not. So once it obtains the surgeon concurrence, it will actually execute the task. So every time the it will ask for surgeon concurrence. And as a result, it's not fully autonomous; it's semi-autonomous. Right? Most of the time, it will be pre-programmed. It will be controlled by the surgeon. But in case if it has to do something on its own, it will still ask the surgeon's concurrence before carrying out this task. The second be teleoperated control. So this does not have any level of autonomy. It's fully controlled by the surgeon. And this is how it is being controlled. The surgeon specifies the desired motion directly through a separate human interface device. And the robot moves immediately. Like for example, the robot will be at the surgery desk and surgeon will be at a workstation. And the surgeon will be controlling a master device. So this is surgeon. And over here we have a robot. And this would be the surgery table. And the robot, this actual robot would be a slave device. It will be a slave to the master, actually. The master device that is being controlled by the surgeon actually. And most of the time, this will be a scaled down version of the surgical slave robot, right? The master robot would be more or less a scaled down version of a uh, scaled down version of the slave surgical robot, right? And that leaves to us to the second statement. Although physical master manipulators are most common input devices, other human interfaces are also used, notably voice controllers. So typically, the slave surgical robot is controlled by a a master robot, which is controlled by a surgeon, and that need not be the case always. The slave surgical robot can also be controlled by voice controlled by the operator. But one important thing to notice is that each and every motion or each and every task of the slave robot will be controlled by the surgeon. It does not have any level of autonomy. The third being hands-on compliant control. So it states the surgeon grasps the surgical tool held by the robot or a control handle on the robot's end effector. The force sensor senses the direction that the surgeon wishes to move the tool, and computer moves the robot to comply. Like for example, in case of in some surgical applications, maybe something related to bone, bone surgery, or uh, things like that. Sometimes the tool would be too heavy for the surgeon to support, right? So in that regard, it can actually take a use of a robot, where the robot will actually hold or position the tool for the surgeon. The surgeon will only need to exert a very minimal force onto that system so that the robot can actually position that tool for the surgeon, and the surgeon actually can make the precise movement. Precise it can Surgeon basically can locate the precise. It can help the robot to to pinpoint the end effector or pinpoint the tool to the precise location, you know just by grabbing that tool and you know control handle and taking that to that specific so that is what it is about, this hands-on applied control. Yeah, so that leaves us with we have covered more or less the entirety of topics for week 8. Now we'll solve some sample problems. And since the topics are all descriptive, I'm not detailed, fully going through them in detail because these are all self-explanatory. But anyway, we'll solve some questions. So the first question is something blank. The surgeon specifies the desired motion directly through a separate human interface device, and the robot moves immediately. So yeah, we have seen this just now because we have seen three different control paradigms for surgical robots: pre-programmed, semi-autonomous, or teleoperated control, or hands-on compliant control. Right? And the question asks the surgeon specified the desired motion directly through a separate human interface. And each and every task of the robot is fully supervised by a surgeon. So like we can eliminate all this all the options that contains autonomy, semi-autonomous, autonomous intelligence, or we can eliminate all these things. So the only sensible option that we are left with is, teleoperation or teleoperated control, because each and every task of the robot is, fully controlled by the surgeon itself. It's apparent from, this control paradigm. So that makes option B the correct answer. And for question 2, it says the robots in which wheels are mounted at the end of the legs is called blank. These wheels can be active or passive to provide more options for terrain-specific mobility. Right? So, like there are robots, for example, if you consider this to be the robot chassis, and if you consider this to be an articulated leg, each and every joints are actuated using motors. There are some robots where at the end of each of these articulated legs, they actually have wheels. right? So when the surface is flat enough, they can switch to wheeled locomotion that is much more efficient than legged locomotion. And when there are obstacles, they can actually lift up these legs to, counter those obstacles, right? And these kind of systems or these sort of locomotion is called articulated wheeled robots, right? It has wheels at the end of articulated legs. And sometimes these wheels can be passive because they may not be powered, they could be simply passive. And in some cases, they could be active. They are also driven by an independent motor. So that makes option B the correct actually. So here also you can see some examples actually. So if you can see this robot has wheels uh, at the end of their legs. And this is a humanoid robot. And during its walking phase, it walks just like any other humanoid robot. These are its feet. And when it encounters a surface that is flat enough for it to move, it will switch to legged locomotion, sorry, wheel locomotion. So there are wheels at its knees and at its toes, right? So when it is at this configuration, it will be supported by four wheels, and it can, navigate as such using wheels alone. So that makes them inherently efficient, as well as much more adaptable compared to either wheels or legs alone. So option B is indeed correct. Going on to question 3. So blank or something is capable of navigating an uncontrolled environment without the need for physical or electromechanical guidance device. So guided vehicle, remote control vehicle, manual cart system, it has something to do with automated guided vehicle or AGVs or autonomous mobile robots, AMRs. So AMRs are actually intelligent enough, they can navigate on their own without the need of any predefined paths. Whereas in case of AGVs, they are only deployed on a controlled environment, and their paths or their field of movement is already predefined to them. And out of these options, which of them is most suitable? It says capable of navigating an uncontrolled environment without the need of any physical or electromechanical guidance device. So the best option would be AMRs, because they can be deployed on uncontrolled environment, or they can be deployed onto an open field, and we don't have to specify the on which it is, through which it should be moving. So the correct option is indeed final option F, right? Yeah, and moving on to question 4, full form of AGVs. It's straightforward. It's automated guided vehicle. So that is also option F. Moving on to question 5. A blank is a robot that is intended to operate with dexterity in a workspace larger than that of a fixed base manipulator, right? So a fixed base manipulator has limited workspace, right? And a mobile robot does not have any dexterity at all because it's just a mobile platform. What about wheel mobile robot? So these are more or less the same thing. What about a legged robot? Legged robot does not, unless it has a manipulator, we cannot comment anything about dexterity. Aerial robot, again the same case, unless it has some sort of a manipulator, we cannot talk about dexterity. What about in the case of a vehicle manipulator system? Right? So we have a vehicle, and on top of this vehicle, we are basically attaching a manipulator. This vehicle can be anything. It could be, wheeled, legged, or it could be underwater, or it can even be aerial. So yeah, so these things, a manipulator that is mounted onto a vehicle, that can have the same dexterity of a typical robotic manipulator. But in this scenario, the workspace would be much larger than the fixed base case. So if the the base is actually fixed, the workspace would be pretty much limited. But if the robot is actually mounted on a vehicle, the workspace can be moved appropriately. So that makes it unlimited. So in that regard, the correct answer is indeed vehicle manipulator system, right? Yeah. Okay. So now we move on to question 6. Earlier was question 5, now question 6. So blank allows the robot to have periods of operational independence subsequent to coordinating their selection of tasks or roles. So, like we have discussed the control architectures various uh, uh, of various kinds. Actually, we have seen the collective swarm systems, and on intentionally cooperative systems, we have seen strongly cooperative, and we also have seen weakly cooperative, which was weakly cooperative. Yeah, and if you can recall, only weakly cooperative out of these three options would allow, subsequent period of operational independence. Sometimes when the robot will have to carry out its tasks on its own without getting any prior approval or commands from the subsequent robots or the rest of the robots, it can do so. Making them operate, independent, making them operate independently. So that makes them a prime candidate for the option would be weekly cooperative solutions. You can actually go through the slides. So these were the different, implementations of a multi-robotic system. And if you can recall, the basic functionalities of how a weekly cooperative system works, they can actually have. This is about collective swarm systems. We have also covered essentially cooperative systems. And if you consider the case of weakly cooperative systems, they can have periods of operational independence, right? And other things also, can deal with heterogeneity, and how their coordination is much different from collective swarm approaches because the robots are not interchangeable because of their heterogeneity. So yeah, the correct answer is indeed weakly cooperative solutions. Moving on to question 7. Fixed wing aerial vehicles require runway. They may stall and need aerodynamic designs. Is that true or false? Fixed wing aerial vehicles like a regular aircraft, so like helicopters and maybe jets with thrust vectoring, all these things can take off most probably vertically like this without the need of any runways. Whereas in case of fixed wing aircrafts or aerial vehicles, they need a runway to generate the sufficient amount of lift so that they can take off. Right. So that is true for fixed wing aerial devices, and they need runway of adequate length. Yeah. If you can recall the slide from week 7, fix that we also cover different kinds of unmanned aerial vehicles, UAVs, which are fixed wing. They have helicopters, we have multiple rotors, we have wings, inspired from nature, just like how birds are flying by flapping wings. And out of these, fixed wing requires, larger uh, runway or requires runway. Whereas in case of helicopters and the, drones with multiple rotors, they can, afford vertical takeoff and landing. And as a result, they does not require any sort of runways. So this mostly is applicable for fixed wing uh, unmanned aerial vehicles. So that makes this option true indeed. Okay, going on to question 8. In one of these approaches, each robot oversees the action of a relatively small group of other robots, each of which in turn oversees yet another group of robots, and so forth, down to the lowest robot, which simply executes its path of the task, its part of the task. Right? Just like how we have seen. At the top, we have maybe a top level robot, and it will delegate its tasks to robots at its lower level. And this basically goes on until it reaches the lower most level. And this is, analogous to the hierarchical architecture that we often see in military commands. So that makes option 3 the correct answer. And if you can recall, the slides from the lectures, the various control architectures for multi-robotic system comprises of centralized, hierarchical, decentralized, and hybrid uh, architectures, out of which the question mostly fits for this hierarchical architecture. The robot basically delegates action to a relatively small group of robots, each of which in turn oversees yet another group of robots, and so forth. Yeah, and decentralized. So indeed, the correct answer is indeed option C. Now, moving on to question 9. The rehabilitation robotics has been defined a special branch of robots which focuses on machines that can be used to help people recover from severe physical trauma or assist them in activities of daily living. So rehabilitation does not necessarily mean limb rehabilitation. It could mean a lot of different things. It could be emotional rehabilitation, mental rehabilitation, all those things. So anything that helps people recover from physical trauma, be it, limb functionality, or be it, improving mental health, all these things comes under the term rehabilitation. So robots deployed for rehabilitation are mostly intended for recovering people from severe physical trauma or assist them in activities of day-to-day living. So that also makes this option true. Whatever is being said is basically true. Yeah, moving on to question 10. In one of these solutions, a large number of homogeneous robots executes their own task with only minimal need for knowledge about other robot team members. So, like out of this, we know where a large number of homogeneous robot is deployed. It's definitely not on weakly cooperative systems, not on strongly cooperative systems. Uh, it's on strongly cooperative systems actually. Question 10. Or I think the more appropriate option would be a collective swarm system, because strongly cooperative can have homogeneous. It does not insist on having heterogeneous, but some level of uh, information about other robots are present in strongly cooperative systems. Right? It knows some level of information what the other robots are executing. But in case of collective swarm systems, it strictly comprises of homogeneous robots, and each and every robot within that system knows uh, very little or very minimal knowledge. It possesses very minimal knowledge about what the other systems or other robots in that systems are doing. So the most appropriate option would be option C, collective swarm systems. Yeah, moving on to question 11. The blank architecture coordinates an entire team of multiple mobile robots from a single point of control and is vulnerable to a single point of failure. So we also know this to be centralized because we have a central uh, point of control which has a good vantage point. It can oversee what other robots are doing. And if one of the robots fail, the entire system basically collapses. So that is a feature of centralized architecture, which we have seen in the slides. And for question 12, something is the most common approach for multi-robot systems and typically require robots to take actions based only on the knowledge local to their situation. This architecture is also highly robust to failure since no robot is responsible for control of any other robot. So basically, this applies to decentralized uh, control architecture, right? Because uh, because each of these robots take action on information only known to them. It does not need to know what other robots are doing, right? And this feature makes them highly robust to failure because since that robot is failed, it can be easily roboted by an identical robot. And since other robots are not depending on this failed robot, their functions are not really affected. So that makes them incredibly robust to failure because as a result, no other robot is responsible for the failure of the specific robot. So that makes the decentralized as the correct answer for question 12. And what about question 3? So question 3 states automated guided vehicles, AGVs, are capable of navigating an uncontrolled environment without the need of a physical or electromechanical guided device. So this is false because statement is only true for AMRs, not for AGVs. AGVs are deployed on highly controlled or highly regulated environments, right? And it also requires some sort of a guidance device for it to, navigate along this environment. So the answer is indeed false. Question 14, select the wrong statements regarding autonomous mobile robots and automated guided vehicles. So we'll go with one by one on all of these options. AGV requires fixed routes. So that is true. AGVs have high flexibility. That is false. Because AMRs can have higher flexibility, AGVs are mostly configured to do a specific task. Third option says AMR are more suitable for traditional businesses than agile businesses. So that is also false. So an agile or a highly dynamic business, we need constant reconfiguration of the robots involved. And AMRs are easily reconfigurable because AGVs are actually programmed and built to perform a specific task. So in that regard, AMRs are more suitable for agile businesses, not for traditional businesses. AGVs are cost effective. That is also false. So in the long run, AMRs are more cost effective. AMRs are capable of navigating in an uncontrolled environment. That is true. So the question says select the wrong statement. So we have 3 wrong statements. False, false, false. So it's a multiple correct answer question. So option B, C, and D are all correct. Yeah. Question 15 says choose the correct statement regarding legged locomotion. So what does the first option say? Legged locomotion are more efficient than wheel locomotion in engineered surfaces. So that is false. Wheel locomotion are much more energy efficient in engineered or smooth surfaces. Second option says legged locomotion offers high velocities than wheel locomotion on uneven groups. That is true. Third option says legged locomotion consumes less power than wheel locomotion. It's obviously false because legged locomotion has more number of actuators than wheel locomotion. Kinetic control is not sufficient for legged robot. It needs a robust hybrid force motion control scheme. That is also true because in case of wheeled mobile robot, we can also use, you know, a purely kinematic control. Like when the effects due to inertia and masses are all very negligible, if the robot is moving very slow, we can still, deploy a kinematic control. But that is not the case for a legged robot because it's inherently highly unstable. It can collapse anytime. So we need to know the influence of all the external forces acting on it and uh, how the masses are actually moving. The inertia and masses are of the links are also influencing the stability of the robot. So in that regard, a kinetic control is not sufficient. We also need a hybrid force motion control scheme for legged robot. And what about option five? Legged locomotion leaves larger footprint on the environment. That is also false. It's typically wheel locomotion leaves the most footprint. For example, anything that comes under its tire tracks would be fully flattened, which is not the case for legged, legged locomotion. So the correct answers are options this one, B and D for question 50. Okay. So now moving on to question 16. So one of these options allow the robots to have a period of operational independence subsequent to coordinating their selection of tasks. We have already seen this question. The correct answer being weakly cooperative solutions. We have already solved a similar question. Okay, 17 is the periodic contact of legs of the robot with the ground is called as dash of the walk. Static support and dynamic support is not relevant to this question. Zero moment point, biomimicry is also not relevant. The correct answer is actually gait. That periodic contact of legs we have already discussed. How different animals can have multiple gaits. In case of mammal, four-legged mammal, it can have a stance gait. It can have trotting gait. It can have a sprinting gait. All these different kinds of gait or the periodic contact of legs on the robot with the ground. It's we denote it by a term called gait. Yeah. And moving on to the final question, question 18, it says in teleoperator control of surgical robots, the desired behavior of the robot's tool is specified interactively by the surgeon. Right? The behavior is actually specified using a graphical user interface by the surgeon, mostly used based on medical images. The computer fills in details and obtains the surgeon's concurrence before the robot is moved. So, is it true for teleoperator control? So, it basically says like in teleoperator control, once the robot takes the concurrence from the surgeon, the robot will execute the task on its own. And it says that is the case of teleoperator control. So, that is obviously false. Because in teleoperator control, each and every motion or each and every uh, uh, task that is done by the robot is fully supervised or it's fully controlled by the surgeon. But so that makes it false. So in semi-operated mode, the computer once obtaining the concurrence from the surgeon, it can execute the task on its own. That is not the case for teleoperated control. So that makes this option false, which is indeed the correct answer. Yeah, so that is about that is the end of today's session. And that is also the end of our weekly live sessions for this 8-week course on wheel mobile robots. And the next week, we may also have one more session, probably during one of the weekdays, so that we can have a summary of all the topics that we have covered, covering topics from week one all the way to weekend for as a single session. If you have any doubts, you can, we can discuss that during that session. The dates will be announced later. Yeah. So until then, thank you. I'm stopping this session right now. Thank you.